Um, so I left something unfinished yesterday, which is let me just say what we had yesterday. So is that legible? Sorry. Oh, it's got to be switched. Ah. Uh-huh. So yesterday we had the notions of the p symbols, which looked like, 1 to the some number n1 and then plus or minus, let me just say e.g. 3 to the n3 plus or minus 9 to the n9 plus or minus. Well, that was the 3 symbol. In the case of the -1 symbol, it was just plus to the n plus minus to the n minus. And then, and what that said is, your Jordan decomposition, your form is a direct sum of an n1 dimensional form in which none of the diagonal form in which none of the entries is divisible by 3, and the cofactor is a quadratic residue or non-residue according to that sign, mod 3. And similarly, it's 3 times a form of dimension n3 and so on. And that completely classifies the 3-adic integral behavior. And this, which is just the signature, completely classifies the -1-adic integral behavior, that's to say the real behavior. But then for p equals to 2, we had 1 to the n1 plus or minus sub t1, and then 2 to the n2 plus or minus sub t2, and so on. The ti is either infinity, and that means that f1, or let's say fq, is type 2. Well, I'm sorry, or that's to say even. And that means it's got even diagonal entries, but nonetheless, its determinant is odd. That's a thing. Or else, or some kind of t, and then it has an odd entry, diagonal entry, and can be diagged. And so can be diagged because it's easy to prove that if a form whose determinant is odd has an odd diagonal entry, then you can still diagonalize it. So can be diagonalized, and T2 in this case is the trace. Or I used to call it the oddity, and in my book with Neil Sloan, we were still calling it the oddity. But the diagonal trace, it's not the trace, if you take the trace, it's not an invariant. Okay, oh, and this, by the way, is mod 8. It's only meaningful mod 8. Infinity is not really a symbol, it's just a way of saying that it's not a type 1. Oh, well, this has an odd diagonal entry, and that's the same thing as saying type 1, or odd. Because conventionally one says an even form is one that represents only even integers, and an odd form represents an odd integer. We're talking about FQ. Then the entries are all multiplied by 2, so it's actually 2FQ, which is part of the form, is actually even, whether this is odd or not. Okay. But then what I didn't say is, but those where invariance of the Jordan constituents, which are QFQ, not of F. Well, I mean, the whole aim is to find invariance of F. And so, you know, why on earth did I write all those? Well, they are at least invariants of the Jordan decomposition. But if you take the Jordan decomposition for any other prime, then the invariants of the Jordan decomposition are invariants of F. But 2, of course, behaves especially. So here's what we can do. Let me just give you a little example down here. Let's take this form. 1, what do I want? 12. No, I think I'll put 6 here. 1, 6. Let's look at 1, 6. Well, that's 1 to the 1 plus sub 1, because the trace is 1. 2 to the 1, well, sub 3. This is 2 times, I mean, the F1 is 1 and F2 is 3. Remember, the Jordan decomposition, I write it as 1 times F1 plus 2 times F2. So the diagonal trace here is 3, and 3 is congruent to 8n plus or minus 3. That's what the sign is. So the sign is minus. I mean, 8n plus or minus 1 means plus and so on. But look, this represents 7. I mean, at E1 plus E2. And so is equivalent to, over the rationals even, and therefore over the quadratic rationals, to 7 something. And what's that something? We can fill it in by the determinant. This determinant is 6, so I want the determinant to be 6 again. Well, now this determinant is 6 to within squared factors. It's 6 times 7 squared. So that form is equivalent to that form. And what's the symbol for that? This is 1 sub 7 to the 1 plus. Here's F1 is 7 now, and F2 is 3 sevens. 21 mod 8 is 5 to the 1 minus. So, you know, there is one Jordan decomposition for this form. Here is another, 2 inequivalent Jordan decompositions. Or should we say 2 equivalent Jordan decompositions? I mean, the terms of this Jordan decomposition are not equivalent to the terms of this one, but the form is the same. So somehow this means the same thing as this. Okay. And this is a case, well, this particular case, let me say this case is solved by what Sloan and I called oddity fusion. Both of those symbols, what you can do is write the total oddity down here. 1 plus 3 or 5 plus 7. So what I'm trying to say is what we get is 1 to the 1. The actual symbol for this thing that I would use, subscript 4. So what I'm saying is, under certain circumstances, I can not write the individual oddities. I need not write the individual oddities. I only need to write the total oddity. Now 1 plus 3 is 4. And 7 plus 5 is 4, mod 8. Remember, these things are only defined mod 8. And so these both correspond to this symbol. And in general, it's okay to replace let me say q to the something, and then 2q to the something, and 4q to the something, and then this is T1, T2, no, so this is, let me make these U, V, W by Q to the something, 2Q to the something, 4Q to the something, subscript U plus V plus W, provided that they're all odd and consecutive. They're all odd forms. So, in other words, what's an odd form? An odd form we can recognize from the fact that the subscript is finite. Okay, infinity is just a way of telling that that's an even form. So, provided all these numbers are finite for a consecutive lot of powers of 2, then you can just replace it by that. This loses no information. Okay, so that's one of the principles, that allow us to change a Jordan decomposition. We can have two different Jordan decompositions. Are they Jordan decompositions of the same form? Well, if they're related by this oddity fusion, yes.
Is there anything special about the real terms there?
No, any number of terms. But they must be consecutive, and consecutive means, for instance, even if F2 doesn't exist, then it's type 2, because it doesn't represent any odd numbers. If F2 is zero-dimensional. But then 1 and 4 are not adjacent. Because they're not adjacent powers of 2. There's a certain subtlety about this. I'm not going to concentrate on the subtleties because, you can see either my book with Sloan or my sensual form book to see what happens. So the other principle is sign walking. And let me give you a little example of that. This time we might have, say, this, and well, I think 1. I'm sorry. No, let this be -1. That's a bit better. So it's not a very good example. So, -2. So this is F1. It's 2, 1, 1, 2. And F2 is 1. -1. Because, we take the factor out, the factor of 2 out. Okay. And what's the shape of this? Well, the dimension of it is, the scale of it is 1. Its determinant is odd. The dimension is 2. The determinant is 3, which is plus or minus 3 mod 8, and therefore the sign is minus. And it's a type 2 form. And here the scale is 2, the dimension is 1, the trace is -1 mod 8, which I shall insist on writing as 7, and then that's a plus, because it's plus or minus 1 mod 8, and that's the correspondence of plus. And now we can do something else with it. I was going to sort of transform it the way I did the other little one for you. So this JD, this Jordan decomposition, is 1 to the 2 minus sub infinity, 2 to the 1 plus sub 5. But it has another. So, okay. Sorry, sub 7. But it has another, which is 1 to the 2 plus sub infinity, 2 to the 1 minus sub 3. I could do a little calculation to just verify that, but let's not bother. It's not worth it. And what's the relationship here? We've changed both signs. So we changed minus on the one part to plus on the one part, and plus on the two part to minus on the two part. And let me say paid for to the subscript. I replaced 7 by 7 plus 4, which is equally 7 minus 4, since we're working mod 8. And that's what, so both signs, and that's what you can do in general. If can do for FQ and F2Q, they're adjacent forms, notice, one of them is for a power of 2 and the other is for the next power of 2, provided that either is type 1, which means odd, provided either is type 1. And if it's type 1, the subscript is finite, and so it can accept 4. Okay, so that's a way of remembering it. So what's happening is these two principles of oddity fusion and sign fusing, they can only happen if something or other is a type 1 form, is an odd form. If one of the Jordan constituents is odd. If both of them are odd, you can fuse the oddities. If one of them is odd, you can change it and an adjacent form. You can change the signs and change the subscript by 4. And that's the end. Let me say that's all, folks. And I hope you understand what I mean by that. What I mean is, if you can get from one symbol to another by just those moves, then the two forms are equivalent. And if the two forms are equivalent, you can get from one to the other by just those moves. So this is the final answer. It's a very funny answer, you may say. You may not like it, but this is the answer, whether you like it or not. Nothing less is the answer, and nothing more is the answer. So if you really want to know whether two quadratic forms are in the same genus, this is the answer. This is the answer. What's so special about the genus? That means that they are p-adically equivalent for each p. Well, there are lots of things that are special about the genus, actually. One thing is that what was I going to say? One thing is Eichler's theorem that you heard John Hankey state yesterday. Whether you took it in or not, I don't know. I shall suppose you didn't. That's a wise supposition, isn't it? I mean, of course, some of you can feel, please, that remark didn't catch me. I was listening at any rate, but I know the people next to me were whispering. But anyway, so Eichler. Eichler says the spinor genus. Now, that's not the same as the genus. Is the answer. That's to say, it's equivalent to the class answer for indefinite forms. Well, they usually say it's indefinite forms of rank at least 3. And rank is really the dimension as far as we're concerned, because we're not allowing the things to be singular just because they're not interesting. Then also there's a theorem of Watson. The spinor genus genus is almost always equal to the genus. Now, I've credited this to Watson so that you'll know, where the credit for this theorem lies. But Watson proved it in various forms. But Conway and Sloan did. We produced a criterion which is really quite easy to state and gives you an exact condition. Okay. In fact, if not, then 4 to the n to the integer part of n over 2 times the determinant is divisible by k to the n choose 2 for some, this is quite a precise and petty statement, you might think, for some non-square number k that's congruent to 0 or 1 mod 4. The square brackets is the integer part of n over 2. Okay. Now, so let's see what happens. It's congruent to 0 or 1 mod 4, but it's not a square, so it's not 0 or 1. It's not 4, because that's a square. It might be 5. Next number is 8. Okay, so let's ignore this thing here for the moment. The determinant, this is really converting from the determinant to the discriminant that some people use. The discriminant is divisible by the n choose 2th power of some number, which is at least 5. So let's think of that. You've got a 10-dimensional form, let's say. 10 choose 2 is 45. The 45th power of some number divides the discriminant. If a 10-dimensional form is, if the spinor genus matters, if the difference between the spinor genus and the genus matters. It doesn't happen very often. Okay. What happen? Let me take n equals 3 for a moment, and then n choose 2 is 3, so it's not all that big. And n over 2. So we say, so let's take the first case was when k was 5. If 4 to the 4 doesn't matter now, 5 cubed has to divide the determinant, or some larger prime cubed has to divide the determinant. That's one case. Another case is that 4 times the determinant is divisible by 8 cubed. 8 cubed is 512, so the determinant itself is divisible by 128. Okay? What happens if the spinor genus isn't the same as the genus? If you're in the bad case that you don't understand, then the determinant has to be divisible by a number which is 125 or 128 or rather bigger. In fact, the smallest case that this isn't a necessary and sufficient condition, but it damn nearly is. If the spinor genus is not equal to if the determinant satisfies this condition, then there's a small multiple of it for which there is a form. So what happens is 125 you actually can't do for a 3-dimensional form. It's still true that the spinor genus is equal to the genus. But 250, oh yes, there are 2 forms of determinant 250 that are in the same genus, but not in the same spinor genus. So the general message of this is you seldom have to worry about the spinor genus. So the genus is the answer, almost always. In 3 dimensions, the genus is the answer for all forms of determinant less than 128. Okay. And as I was saying, for 10-dimensional forms, the spinor genus is the answer unless the determinant is absolutely enormous. Okay. By the way, you can still compute with the spinor genus and so on. We give up, Sloan and I give a sort of algorithm way of doing it in the book. So even when the Spina genus is not the answer, you can you can get the complete classification out of this statement, provided they're indefinite. If they're definite, no, it's much. There isn't really any sense in which it's reasonable to expect p-adic invariance to say what's going on. Okay, that's that. What happens? I think. Yes, I'll do a small determinant. And I'm going to take indefinite and dimension free. So without loss of generality, the signature is plus squared minus to the 1. I might as well make it 2 pluses and 1 minus, because otherwise it's negative, has 2 pluses and 1 minus. Then let me just tell you, so let's take the determinant equals 4. Well, let's take the determinant equals p, and I'll p greater than or equal to 3, and p always means prime for me. Okay, p greater than or equal to 3. Well, the 2 symbol is 1 to the 3. Now, it's necessarily type 1, so I'll put a dot there, which means not equal to infinity. And then plus or minus. And the p symbol is 1 to the 2, p, and then there's a plus or minus, p to the plus or minus, p to the 1 plus or minus. Those are the only possibilities. And perhaps I should just say that the -1 symbol is plus squared minus to the 1. So they determine the genus. Now, how many cases are there? Look, these two, this sign may be either. So there's a choice there. But this one is then fixed, because the product of the two signs is the determinant. Well, it's what's left of the determinant when you struck the p factor out, and what's left of the p factor is the same thing. So in fact, it's the same as the other one. So we've got one choice there. This is fixed. And I should really have written this answer. So the thing that we call question mark is known by the global relation. The global relation says that the sum of the pxs's over all p is 0 mod 8. We know the pxs for here, and we know the pxs for here, so we know it there. So we don't need to bother to specify it. So there are just two genera. And we abbreviate them. We don't have to say all this. Abbreviated 1, 2, 1 of 3 plus, and 1, 2, 1 of 3 minus. In fact, if you know you're in this signature and so on, you can go about all this stuff and just call them 3 plus, or p plus, sorry, and p minus. Okay. The same is true the same true, for determinant plus or minus 2p. The two symbol is determined essentially again. Three symbols determined. The only choice is the p plus or minus. So the abbreviated symbols are 1, 2, 1, 2 times p plus, and 1, 2, 1, 2 times p minus. And in general, these symbols have the property that if you just read the stuff in here, ignoring the frivolous decorations, then you get the determinant. Oh, up to sign. But you can tell the sign because there's one negative one here. Okay. Now, I did with some students, I did the forms of determinant 4. And let me sort of say what they were. What I'm going to write down here is one is the general structure. Sorry. So this is d equals plus or minus 4, but we'll say minus 4. And I'm supposing I'm in the same signature. Well, if these are both odd, then we can fuse their oddities. And now, this is equal to 1 to the 1. Oh, sorry, that was meant to be plus. 1 to the 1 minus 2 to the 1 minus sub this thing plus 4. Okay, so we might as well suppose we're with the signs of plus. And then when I put this dot here, I mean to imply that you don't need to say it because it's workable out. This is the only prime that matters. Okay, from all the other primes, we can work out what this trace is. This trace mod 8 determines the two signature mod 8, and conversely. So there's only one of it, and what an example of it is this one. So this is a form with having this symbol here, and it's the only form having this symbol. If you like, you could make it equal to minus 1, 2, 2, because that has the same symbol. So these must be equivalent, and indeed they are. Look at this. This represents 1, and so it could be rejigged to be 1, minus 2. Okay. Now there's the question. Suppose our 1 part is odd, and our 2 part is infinity. Well, at least one of them is odd. So this is equal to 1 to the 1 minus 2 to the 2 minus sub infinity. The signs are the same anyway. The signs are, these two signs are the same because what that sign is the odd part of the determinant Legendre against 2. So there's only one such form, and an example of it is this one. Now there's the question of a 1 and a 4. What happens here is this. The signs, but they can be sign walked, so we can suppose them plus again. Right, and now this number here must be 1 or 7 mod 8, because in the two-adic decomposition, it's got to be 8n plus or minus 1. So that's forced to be 1 or 7. And then this is just determined, for the usual reason. The global relation determines it. So there's only one possible signature like this and one possible signature like that. And you can't move from one to the other because the only two ways of moving don't do it. These forms aren't adjacent, so you can't fuse oddities. And 1 and 7 aren't congruent mod 4, so you can't do it by sign walking. So one of them is this form, and the other one is this form. It's easy to write down these forms that I'm doing at the right-hand side of the page. It's not perhaps all that trivial to prove that these two forms are inequivalent, but they are. But the real thing that's non-trivial, okay, now we might manage to make this one infinity. Or this one infinity. Now we can't sine walk from here to here because look, the true form is an even form, and therefore there's a true form of dimension 0 that's even, and we can't possibly get to the one form because you can only do a move if one of the forms is odd. So once we've made this an even form, that's the subscript infinity there, you can't sine walk. Okay, but this number is still determined, so there's only one of it, and here it is. You see, this 0, 1, 1, 0 is an even form of determinant -1 and so on, so that's it. Now this one, it's distinctly harder to make this form, and so that's really quite interesting. If you were just writing down forms as sort of very nearly diagonal, you might get these first 5 and then not notice the second one. Well, you see, the point is, what we've got to do is have a minus sign. This is a form of odd determinant, so it's suitable for a Jordan constituent at the 1 part, and the shape of that is 1 squared. The determinant is 3, and then it's an even form. We wanted determinant -4 altogether. How are we going to get that? Well, this does it. No, -12. That does it. The determinant of this is 3 times -12 equals -4 times a square. Okay, so that's a permissible two-adic form of determinant -4. I mean, that's the way we think of it. The determinant is only meaningful mod squares. Now, how do we get from this form? Okay, so let me write its matrix out. A, B, C. How do we get from that form to one whose determinant actually is -4? Well, we take a superlattice of index 3. And so we've got to find something. Let me just tell you what the answer is. Let me write A plus B plus C here initially, and that's 3. 3 minus 12. Those numbers are all divisible by 3. And then I'm going to divide it by 3. So the new vector A plus B plus C over 3 has those inner products. It still has integral inner products with the old 3. And here it is again. Damn it. Damn it, the sign doesn't work. Well, I'm sorry, I thought I was so clever doing this example. But I wasn't. I see. If I had done that, then I could do this. This plus this over 3 is 6. So what happens? So I'll do this one, but it happens to be positive definite. You see, I take the new lattice generated by all 4 of these vectors, but this one shows that C is redundant. And now I've got this ground matrix. Okay, so this is This is a positive definite form with whatever it was, with what we wanted. 1 to the 2 minus sub infinity, 4 to the 1 minus. And I'm sorry, that wasn't it. I didn't notice that I changed the sign there. But you can do it the same way. It would take me a few minutes to find it, so I'm not going to find it in public. So anyway, what one can do here, there are 6 forms of determinant minus 4 indefinite dimension 3, okay? The fact that I couldn't work out the last one doesn't matter very much. And so in principle, I mean, that shows you what the classification looks like. One can, it's messy, it's combinatorial, but you know what these symbols are for the genus. You know when 2 symbols for the genus are equivalent, although that's a bit messy. You know precisely when there is a form corresponding to a given thing. It's only if it satisfies the global relation. And you know by Eichler's theorem, supplemented if necessary by Watson's thing, that unless the determinant is terribly complicated, has a huge power of P in it, the form is unique. So that's that. Okay, now by the way, let me find out what the time is. Well, okay, 5 minutes. Well, let me say some other things. What's the use of this? Well, I'll give you a few applications of being able to classify things and being able to restrict things. One is a really rather nice one, the Brooke-Reiser theorem. So this is about projective planes. It's terribly hard to find when projective planes exist. A projective plane is a thing in which there are things called points. This is a sort of purely combinatorial projective plane. There are things called lines. Any pair of lines intersecting one point and various other stuff. And it's possible to have a plane we say the plane has order R if there are +1 points per line. And I'm going to write down the lines corresponding to rows and the points. And this is the incidence matrix. And I'll say, this line, etc. There's R+1 ones in this incident matrix. And then there's R+1 ones in this one too. Okay. But there's just one in common, because these 2 lines have got to intersect in one point. Okay, so this is the incidence matrix, which is usually called A. And this condition tells you that A transposed is, well, the inner product of this with itself is R+1. So there's R+1 down the diagonal and 1 everywhere else. Okay? A transposed tells you what the inner products of the lines with each other are. Anyway, the point is it's known. That's all we need to know, and we can work over this. And rather than doing this, I can regard this as A times the identity matrix times A transpose. But this kind of thing says that the quadratic form with the identity matrix, which is the sum of squares form, is equivalent to the quadratic form with this identity matrix. So they must have the same invariance. Aha. Well, it turns out that they don't unless, how can I say it? If R+1 is 0 or 1 mod 4, it's got to be a sum of 2 squares, turns out in the end, is a condition for this. So it's a sort of obvious thing to do. You take the condition on the identity matrix, you interpret it as a statement about quadratic forms. The 2 quadratic forms are equivalent, and they aren't sometimes, unless R has this very special form. That's a very famous, remarkable thing. There are other places where the quadratic form is an invariant and so on, but anyway, that's that. Let me tell you about knot theory. There exists a quadratic form for a knot, which it's changed its definition over the years. But this quadratic form is basically computed from the intersection numbers of the homology classes on a Seifert surface. And it's not quite invariant. It's invariant up to addition of of hyperbolic planes. The addition of, if you add a new handle to your surface, that turns out to add a hyperbolic plane. However, that's the precise condition. You know, they're either straightforwardly equivalent as quadratic forms, or they're equivalent up to addition of hyperbolic planes. So in other words, they're equivalent in the Wittring. Now, equivalent, let's think what happens when you add a hyperbolic plane. You make it indefinite, and you make its dimension at least 3. Okay, so the spinor genus is all you need to answer. Moreover, if you add lots of hyperbolic planes, you've made its dimension very large, but you haven't changed its determinant significantly. You might have negated it. And therefore, you can take it up to a form where the spinor genus is equal to the genus. So, and by Eichler plus Watson, the genus is enough. You understand me? And by the way, that's a remark of Kneser. I said that my initial reason for studying quadratic forms was from knot theory. I didn't understand at the time. These stuff wasn't quite available. Eichler's Kneser's contribution and so on. I didn't understand at the time exactly what the addition of new rows was doing in the quadratic form. But it's really nice to know that the purpose. It's nice for me to know that the purpose for which I studied quadratic forms, the only thing you need to know is the genus, and I know the genus now. Okay, I think I'll stop.